That's the example we just discussed. The second half of this example is about this question. If I now take a third vector, fifth vector, and I call it vector A, with the components 8, 9, and 5, I'd like to address the question about the spans, which I discussed with you with the corollary. Now we have a chance to practice that. We will develop this example. And now I'd like to ask the question when and whether this vector is in the span of my v1, v2, v4, v3, v4. Okay? I want to test if my A is in the span of these 4 vectors. If I test for that, I have to answer the question whether I can solve for the coefficients lambda 1, lambda 2, lambda 3, lambda 4, such that the combination of my v vectors with these coefficients delivers the vector A. Again, computationally, this is solving of system of linear equations, another augmented matrix, another row echelon form reduction. Given that I'm recycling or reusing the same computations as before, it will be the same augmented matrix like in here. So you don't have to copy that. The only difference will be that to the right of my augmented matrix, we will have this extra column, 8, 9, and 5. Here it is. It's the same matrix as in here, but with extra column 8, 9, 5 on the right-hand side. The same set of operations will work by taking my matrix to the row echelon form. So here we go. If I take my matrix to the row echelon form, here it is. This time you see I cancel out 7. This time I cancel out 7, so it's the same matrix with one extra step, one extra operation when I cancel the 7. And here's my right-hand side. Our study of system of linear equations from the first semester told us that this system will be solvable, right? We don't have a pivot on the right-hand side. It's 0 here. So the system is solvable. So the answer to the question whether my A vector is in the span, the answer is yes, it is. Let's just find the solution. Let's just find the actual values for my coefficients here, which will bring my A vector in the span. And this time, I will present the general solution. So I will parameterize these 2 columns. They are non-leading columns. Here's my parameterization. Lambda 3 will be T. Lambda 4 will be S. Here's my parameters. If I solve for lambda 2, from this line, it will be 3. Take T, take S. If I solve for lambda 1, from this line, it will be 8 take double S from here, take 4t from here, take 3 times the coefficient lambda 2, that's the whole thing. If I do the expansion, at 8 take 9, it's negative 1, take t plus s. Here's the expansion. Here's a complete general solution to my system of linear equations and the complete set of coefficients which make this happening. If I sub in my coefficients, here they are. If I sub in my coefficient, that's the expression for lambda 1. This is the expression for lambda 2. Here's the expression for lambda 4 and lambda 3, lambda 4. Yeah. And that answers the question how to express my A vector in terms of v1, v2, v3, v4, and why A vector is in the span. Now, I will take this one step further by making this observation. I can rearrange the terms here a little bit. I mean, the first thing I say is this. The representation of my A in terms of v1, v2, v3, and v4, it's not unique, right? Any choice of TS here will produce a representation. Any choice of TS will produce a representation. 1, 0, 0, 0, 0, 1, 1, 2, 3, 4, any choice of TS will make a representation. However, if I now expand everything, and if I try to cancel T and S, look what happens. I will combine all of the vectors with no T on S, so it will be negative 1 v1 and plus 3 v2. And then vectors with T coefficient, they will be T comes with a negative V1, right? Negative V1, negative V2, and positive V3 is the thing in front of T, and S comes with these vectors, plus V1, take V2, and plus V4. Here's my rearrangement. And if you look back what we did before, if you look at these two lines, we discovered with you before, it means that this bracket is 0, and this bracket is 0. It's something we established before with you, meaning that the same A can be expressed with no T and S as this, and that's now a unique representation. So it's another idea which I present on the slide, is that if vector comes from a span of other vectors, if they are linearly dependent, there will be multiple representations. But as soon as you single out the linearly independent subset, as we now know we can always do that, with one exception from the previous slide, the representation in terms of the linearly dependent vectors will always be unique.